10 years ago, the scientific consensus on climate change was confident but cautious. Researchers warned of a warming planet, but often framed their predictions as highly probable rather than absolute. In 2014, the Intergovernmental Panel on Climate Change, or IPCC, the UN body responsible for assessing climate science, stated that human influence was clear. By the time they released their sixth assessment report in 2023, the language had hardened. The word likely was replaced with unequivocal. The data shows that human activities, primarily the burning of fossil fuels, have heated the global surface temperature exactly 1.1 degrees Celsius above pre-industrial levels. This graphic is known as the climate stripes. It visualizes global surface temperature changes over time, with each stripe representing a single year. Notice the far right side of the graphic. The dense, dark red bands represent the years between 2011 and 2020. This 1.1-degree shift acts on global systems like a physical force, displacing weather patterns and ocean currents simultaneously. This concentration of heat marks the most rapid acceleration of warming we have on record. The last decade reveals that Earth's natural systems respond to even small increases in heat with rapid, large-scale changes. To see where that atmospheric heat actually goes, we have to look at the oceans and the cryosphere, the frozen water parts of Earth. Since the 1970s, the global ocean has acted as a massive thermal sponge, absorbing 91% of the entire climate system's excess heat. This chart tracks global mean sea level rise. As water warms, it physically expands, and combined with melting glaciers, the rate of sea level rise accelerated sharply between 2006 and 2018, reaching 3.7 millimeters per year. With a higher baseline water level, routine tidal patterns and seasonal storms easily overtop coastal defenses, compounding into severe flooding hazards for communities. The oceans now function as a thermal battery, releasing this accumulated energy back into the atmosphere and fueling more intense storms. That kinetic energy doesn't stop at the shoreline. The ripple effect moves directly inland, striking the terrestrial biosphere. This burning embers chart maps global temperature increases against climate risks. Comparing 2014 data to the revised 2023 models reveals a stark contrast. The new models show the red and purple zones, indicating very high risk, sliding downward, overtaking the 1.1-degree mark we are already living in. This drop in safety thresholds correlates directly with what biologists are observing on the ground: the rapid breakdown of local ecosystem structures and widespread biodiversity loss. The buffer zones we calculated for terrestrial life 10 years ago were incorrect. Under the weight of current data, those margins of error have vanished. These collapsing ecological buffers immediately expose the sprawling human infrastructure built directly inside them, removing our natural defenses against extreme climate shifts. A measured drop in total column soil moisture, the water held from surface to bedrock, coupled with extended heat waves, directly destabilizes agricultural yields and global water security. The burden of these failing systems is highly unequal. Vulnerable communities, who contributed the least to global emissions, experience disproportionately severe losses to their homes. Waiting to adapt creates a new hazard: locked-in infrastructure. Delaying modernization forces future generations to rely on aging, high-emission facilities, failing to meet their needs. The data confirms that warming is a present-day destabilizer, steadily eroding the economic and societal bedrock we rely on right now. To map out how we survive this, researchers use shared socioeconomic pathways, or SSPs. These are projected scenarios that model different baseline futures based on our choices today. This dual-axis chart illustrates a crucial economic shift. The market costs of photovoltaics and wind energy have plunged sharply, becoming cheaper than fossil fuels. Simultaneously, global adoption rates for renewables and electric vehicles surge exponentially upward, proving a structural shift. We now possess both the technological capability and the financial maturity required to transition the global economy and achieve net zero carbon dioxide emissions. Transitioning to a stable climate depends on execution speed and political will, as the technical solutions are already proven and cost-effective. The IPCC outlines a comprehensive strategy to manage this transition, called Climate Resilient Development. It fuses aggressive emission cuts with the active protection of our remaining natural ecosystems. The science is explicit. Conserving 30 to 50% of Earth's land, freshwater, and ocean areas is a non-negotiable prerequisite for maintaining human survival. But our window to implement this is closing. Every additional fraction of a degree of further warming permanently restricts our future options and makes adaptation far more expensive. Because the planet functions as a single system, the response in this decade requires immediate, unified action across every sector.